Hello everyone, I'm Wang Pingping from midas, China. Today, the topic of my report is stability assessment of dam design using Multiphase flow analysis. I will introduce it from the following three parts. Part 1, brief introduction of dam design. Part 2, introduction of actual case of dam break. Part 3, simplified dam break model demonstration. The laws of hydraulic structure can be divided into permanent load, variable load, accidental action. First, permanent load, including the weight of the structure, soil pressure, surrounding rock pressure, and so on. Second, variable load, including hydrostatic pressure, hydrodynamic pressure, soil pore water pressure, and water hammer pressure. Third, accidental action, including water weight during flood discharge, wave pressure, and seismic action, and so on. It can be seen that most loads are related to water. Generally speaking, CFD method should be used for analysis involving water. However, some conditions, such as hydrostatic pressure, can be calculated by empirical formulas. As shown in the figure, if the water level fluctuation is small, the hydrostatic pressure formula can be used to calculate the water pressure. However, if the water level fluctuation is large, empirical formulas cannot be used. At this point, the CFD method needs to be used to calculate the free surface. Similarly, seepage calculation has been widely applied in dam design. This is the GTS. But the premise is that Darcy's law needs to be met. Working conditions such as dam break and flood discharge clearly exceed Darcy's law, and the CFD methods are required at this time. In the field of hydraulic engineering, the flow in canals, rivers, and the steering basins, as well as the flow around ships, are all examples of flow phenomena involving free surface. The determination of the free surface of water flow is one of the more complex problems in the numerical calculation of fluids. Due to the unknown shape of the free surface in advance, the free surface problem is a strongly uncertain boundary problem. Under different circumstances, different assumptions, and the treatment methods are used to treat the free water surface in open channel flow. First, for fluid flow analysis in open channel with predictable water level, general fluid flow analysis can be used, such as local river channels, small-scale channels. Second, if we want to simulate the change in water surface in our calculation, two fluid media needs to coexist in the computation domain, namely air, and water. At this time, a Multiphase flow method is needed. It is the calculation of the mutual disturbance between the gas and the liquid phase between air and water, the capture of the phase interface, and the flow state of these different phases when passing through the solid boundary. Midas NFS has two methods for calculating Multiphase flow, namely VOF and the level set. In conditions such as fluid discharge, dam break, or energy dissipation buildings, the water level fluctuates greatly, and it is difficult to predict the water surface line. Therefore, multiplied flow is required. Usually use the level slip method. Next, we will use an actual case of dam break to understand the multiplied flow analysis using the level slip method. This is a real terrain model. Midas NFX can import real terrain data. Assuming the dam is damaged during the flood season, this case study analyzes the upstream reservoir water flow path after the dam is damaged. Dam break calculation is an effective means to quantitatively estimate the impact of reservoir and that volume and to reasonably determine the flood control design standards and the hedging measure of reservoir or depth. The main campaign of dam break calculation is to calculate the flow quantity and the water level process line of a dam break dam set, as well as the flow quantity, water level, flow velocity along the downstream flow evolution process, and the flood peak arrival time. The model assumes that upstream flow quantity is fixed and there is no additional water source. Therefore, with the passage of time, the amount of water in the model will be less and less. Of course, the inlet boundary condition can also be modified according to the actual situation. It can be seen from the video that the water level process line of the dam break dam thing. Now, let's open NFX. This is the real case. These are their solid domain. We imported from outside. Here, import, select geometry files. But we need to create fluid domain. Using the function make CFD volume extraction. These are their fluid domain. Okay, let's switch to result mode. Here is mesh set. Okay. See the volume fraction. So ISO value surface. Hit default. Move it. We can see the water level lines. Let's view result value of some node or element. Okay, select this node. Click table. Right. Preview. Okay, it can be seen from the figure that the flow peak reached the monitoring point at 18 seconds. Okay, close. Okay, let's see the water flow force on ground. Switch to pre-mode. Extract elements. Okay. Hide mesh. Add phase. Select ground phase. Three objects. Okay. Switch to post mode. Press pressure. We can get the impact force of water flow on the ground.
Add.
Move it.
Delete. The flow quantity of any position
can
can be
see its
extracted.
change.
This. Close it.
Okay, let's view the flow quantity. Flow quantity.
We can also see the flow path.
Flow path. By plane direction.
We can choose the ground phase, and the flow path line is more. Let's see the movie. This is the real case. Finally, I will use a 2D dam brick model to demonstrate the complete process of multiphase flow analysis. OK, open NFX. Create a new document. Select 2D dimension. OK. Click Geometry. Import CAD file. Open it. OK, let's measure the distance. OK, the distance is correct. Close it. Add all gathers. Now, save it. OK, let's define the mesh. Create the CFD material. Choose the fresh water. Click OK. Close it. Define CFD 2D property. Change the name water. OK, close it. Now we can define the mesh size. Choose this edge. We can design the mesh size. Find the mesh size is 0.1. Okay. Now, auto-generate 2D mesh. Select all face. Size is 0.5. Register each mesh independently. Choose this. Okay. Fine. Close it. This is the initial water level. Now we can hide mesh set. Next, we can define CFD boundary condition. In this model, there are only two CFD boundary, outlet and the wall. Now, let's define it. Outlet is this, and this. The pressure is 0 Pa. Okay. Wall is this and this. If default, okay. Now the CFD boundary is defined complete. We can add transient CFD case. Edit it. And size control. Click Advanced Modulus. Choose Multiply Flow. OK. Modulo date. Choose include hydrostatic term. Click it, move it. OK. Now we should define initial condition. Choose Modify. Mesh size. We should define Modify Manager. Use the Modify model is level seed. Material is fresh water. Click OK. Now, edit case. Initial condition. Modifies. Phase 1 is auto mesh 2D is. Okay. Okay. Now we can define the number of steps. Use 500. 5,000. Okay. 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 The case is defined complete. Now we can solve it.
Okay, the solution is complete. Now we can check the volume fraction. Move this. We can see the water level line. And the pressure cloud date. We have defined the safety graph. This is the water level of monitoring point, this point. We can see from the graph that the flood peak arrived at a monitoring point at 1.4 seconds. We can see that max measure is about 400,000. We can check the ISO value service. This is the water level, and we can export the file. And we can draw the chart in Microsoft Excel. We also can see the flow path of the model. We can use the nodes. Every step. And see the movie. Okay, that's all the operation. Okay, the above are all the operations there.
Hello, my name is Colin. I am responsible for Midas NFX sales at Midas IT. I will now introduce the Midas NFX safety capabilities. Midas NFX safety provides various analysis capabilities as seen in the figures. It offers analysis considering all types of fluid domains, steady state, unsteady state, and both compressible and incompressible flow. It provides a total of 14 turbulence models and support GPU calculation in addition to CPU parallel computing. Especially through FSI functionality, it allows for fluid analysis considering structure deformation or moving. You can obtain analysis results more conveniently by using various simplification features that reflect complex real-world physical phenomena. FXCFD allows for simultaneous thermal analysis of both structure and fluid domains. In addition to the airflow around the LED lamp, as seen in the left figure, it is also possible to calculate the temperature distribution of the LED lamp structure. For this reason, NFX safety also allows considering the interconnectivity of mesh generation between each part and supporting contact conditions. NFX safety provides not only conduction and convection models, but also radiation models by default. Moreover, using various simplification features, complex physical phenomena can be easily defined. As seen in the right figure, pulsed convection using a fan can be quickly and accurately modeled with the fan boundary conditions. This simplified modeling approach can have a significant impact on the analysis of long piping systems. Even with a small number of meshing using 1D elements, NFX can produce analysis results that accurately consider real-world physical phenomena in complex piping modeling. NFX safety offers various analysis techniques for simulating rotating objects. As seen in the left figure, using sliding mesh allows for the consideration of the structure's rotation, enabling simulation under real conditions. Conversely, the MRI picture can be used to simulate the effect of rotation without the actual structure rotating by applying a rotational velocity state. Additionally, for cases where another structure within a rotating structure, such as a mixer, is also rotating, analysis can be performed using the overset mesh technique. NFX safety can also analyze the mixing process of different types of fluids. It is capable of analyzing not only the mixing of different types of gases, as seen in the figure, but also phenomena where specific gases diffuse into the air. NFX safety provides analysis that takes into account different phases, such as fluids and gases. For analyzing these scenarios, it offers techniques like free surface analysis and BOF. With free surface analysis, you can observe the behavior of chemical substrate when sprayed onto a vapor surface using a nozzle spray, as shown in the top left analysis case. Additionally, it can be used to analyze the sloshing phenomenon of LNG gas inside an LNG carrier tank during movement. The analysis case in the center of the screen utilizes the BOF functionality, considering level set, to analyze the behavior of fluids with different viscosities. Finally, NFX safety provides particle behavior analysis using the DFM feature. In the analysis case on the right, the results were often using the DFM feature to analyze the particle distribution inside the oil catch can, a component of the car. NFX safety offers these various analysis capabilities to consider a wide range of physical phenomena. With this, I will conclude the introduction to the midas NFX safety analysis capabilities. Thank you for your attention.